Structural systems are generally subjected to various loads. An applied load, regardless of its source or nature, can be classified as either a concentrated or a distributed load. For example, in a bridge structure, a moving vehicle exerts a series of concentrated loads on the bridge girder. The weight of the girder itself, however, is treated as a distributed load. Further, a distributed load can act along a line or on a surface. That is, we have one-dimensional distributed loads and two-dimensional distributed loads. A load distributed over a surface, such as a floor system, is considered two-dimensional. A load distributed along the length of a beam is considered one-dimensional. In this lecture, we're going to examine the analysis of beams subjected to various one-dimensional distributed loads. We could have a uniformly distributed load. This is a constant load. The load magnitude does not change over the length of the beam. A triangular load. In this case, the load magnitude changes linearly with a constant slope. A trapezoidal load. This load can be viewed as a linear combination of a uniformly distributed load and a triangular load. A double triangular load, or a generalized distributed load where the load magnitude is defined using an algebraic function. For our purposes in this lecture, beam analysis involves calculating support reactions and the internal forces. How do we handle these calculations when the beam is subjected to a distributed load? For calculating support reactions, we can replace the distributed load with a concentrated load before formulating the equilibrium equations. For determining the internal, shear and moment forces, however, we should not replace the distributed load with its equivalent concentrated load. If we do, less than accurate results will be obtained. So let's examine each type of calculation separately. First, let's see how support reactions can be calculated when a distributed load is present. To determine the support reactions, we start by replacing the distributed load with a concentrated load called the equivalent concentrated load. Note that a distributed load defines a geometric area. For example, in the case that the load is distributed uniformly over the length of the beam, the load forms a rectangle. Here the base of the rectangle is the length of the beam and the height of the rectangle represents the load magnitude. Since the load magnitude is given as force applied per unit length, then the area of the rectangle, base times height, gives the total load applied to the beam as if the distributed is condensed into a single point load. The value of the total load is indeed the magnitude of the equivalent concentrated load. But if we were to replace the distributed load with its equivalent concentrated load, where on the beam would we place the concentrated load? The location of the concentrated load is the geometric center of the area formed by the distributed load. In this case, we know that the center of the rectangular load is located at the midpoint of the beam, so that is where we place the equivalent concentrated load. Now we're ready to calculate the beam's support reactions by formulating the equilibrium equations and solving them for the unknowns. Here are a few examples illustrating this process. Example 1. A beam is subjected to a uniformly distributed load of 2 kilonewtons per meter. What are the support reactions? The beam is 10 meters long. First, let's replace the distributed load with a concentrated load. The magnitude of the equivalent concentrated load equals to the area of the rectangle defined by the distributed load. The rectangle has a base of 10 and a height of 2, so its area is 10 times 2, or 20. Note that the unit of this force is kilonewton. The equivalent concentrated load is placed at the center of the rectangle, which is 5 meters away from the left end of the beam. As I mentioned before, the support reactions for a beam subjected to the uniformly distributed load are the same as the reactions of the beam subjected to the equivalent concentrated load. So to find the reactions, we can use the beam subjects to the concentrated load. Here is the free body diagram of the beam. The reactions are determined by formulating and solving the equilibrium equations for the unknown forces. Example 2. This beam is subjected to a triangular distributed load. Determine the support reactions for the beam. The magnitude of the equivalent concentrated load equals to the area of the triangle defined by the load. The triangle has a base of 12 and a height of 2, so we can write P equals 12 times 2 over 2, or 12 kilonewtons. The equivalent concentrated load is placed at the geometric centre of the triangle, which is located at 1/3 of the away out of the right angle along the base. Therefore the concentrated load needs to be placed 4 meters away from point B. The support reactions for the beam subjected to the uniformly distributed load are identical to the reactions of the beam subjected to the equivalent concentrated load. To find the support reactions, we can use the beam subjects to the concentrated load. Here is the beam's free body diagram. We then calculate the reactions by formulating and solving the equilibrium equations for the unknown forces. Example 3. In this example, we wish to determine the support reactions of a beam when it's subjected to a trapezoidal load. To find the magnitude of the equivalent concentrated load, we need to calculate the area of the trapezoid. This equals to the sum of the two sides times half of the base of the trapezoid, that is, area equals 1 plus 3 times 12 over 2, or 24. The location of the equivalent concentrated load is the geometric centre of the area, which can be written as x equals L over 2 plus L over 6 times B minus A over B plus A. Since L is 12, A is 1 and B is 3, we get x equals 7. That is, the geometric centre of the trapezoid is 7 meters away from the left end of the beam. So here is the free body diagram of the beam when the distributed load is replaced with its equivalent concentrated load. We can now write the equilibrium equations and solve them for the unknown reactions. An alternative formulation for this problem involves decomposing the trapezoidal load into a rectangular load and a triangular one, such as if we add the triangle to the rectangle, we get the trapezoid. We can then replace each distributed load with its equivalent concentrated load. The rectangular load has an equivalent concentrated load of 12 kilonewtons placed at the centre of the beam. The triangular load has an equivalent concentrated load of 12 kilonewtons as well. This load is placed at the geometric centre of the triangle, which is located 8 meters away from the left end of the beam. Here are the equilibrium equations based for this alternative formulation. Obviously they produce the same support reactions as the original formulation. Example 4. In this problem, the beam is subjected to a parabolic load defined using the quadratic equation Wx equals 2 minus 2 over 25 times x minus 5 squared. To find the magnitude of the equivalent concentrated load, we need to determine the area under the curve. This can be done by integrating Wx. The area is 40 over 3. To find the location of the equivalent concentrated load, we need to determine the location of the geometric centre of the area. This is done using this equation. So the centre of the area is located at the midpoint of the beam 5 meters away from point A. Here is the free body diagram of the beam, where the distributed load has been replaced by its equivalent concentrated load. The equilibrium equations and the support reactions are